And in general, we can define what we call the Nash equilibrium. Basically, it is an equilibrium that describes strategic players' unilateral lack of incentive to move away from this choice. Notice this word equilibrium is not the same as the equilibrium we saw earlier, which used to describe the convergence of iterative algorithm to a particular point. In fact, we later see yet another notion of equilibrium. So more precisely, let's say that there are two users. Okay? And user 1 got utility U1, user 2 got utility U2. And user 1 got a strategy set, script A. And user 2 got strategy set, script B. And we say that a particular point, call that A star, and a particular point B star in A and B sets respectively is called a Nash equilibrium if the following definitions are true. First, the first user's utility at this point, A star, B star, will be no smaller than the utility where user 2 sticks to B star and user 1 is free to pick any A in the set of possible strategies. Okay, that's for all A in the set A. This simply says that, hey, if the other player doesn't move away from B star, I have no incentive to move away from A star. And that's the key word. And at the same time, the other user feels the same way. U2 at this A star, B star is no smaller than the utility for user 2 if A star remains there and B is free to be chosen anywhere in the set. Okay, so this B can be any point in the set. Doesn't matter. What it says is that for user 2, again, I have no unilateral incentive to move away from B star. If the other player sticks to A star, I'm going to stick to B star. And the key thing is that both statements must be true for the single point A star, B star. That's what we mean by matching best responses. And if so, we call this A star, B star point a Nash equilibrium. It says there's no unilateral incentives to change my strategy away from A star, B star. So in this case, there are two Nash equilibria. The action is a Nash equilibrium because neither A nor B has a unilateral incentive to move away from this choice. And there's another Nash equilibrium, romance. And back to the prisoner's dilemma, this confess is the unique Nash equilibrium. Even though both realize it's better to go there, but there's no unilateral, that's the key word, incentive to move away from this point. Basically, A says, if you don't move, I don't move. B says, well, if you don't move, I don't move. And they both are stuck in this socially suboptimal, unique Nash equilibrium.